everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video, this final video of theory for NMR, we're going to start to learn how to put the pieces together. We're going to learn how to interpret charts. Now, it took a long time to get to this part, right? So there's a lot of theory, a lot of details, but now it's time to wrap everything up into the interpretation of charts. Now, I have to tell you, the one important thing that I'm mentioning now is that you do not jump ahead of me. Don't try to solve my example problems, and because if you do that, you're really not going to get the details that I'm trying to teach you. The goal for this video is to teach you different strategies that you have available. So there are different rules or tools that you could use to help make your life easier on your exam. So if you jump ahead and you just try to solve the problem, you're not going to get those rules. You're going to just be too busy, using your own technique. But what you really want to do is shadow me in this video set. You just want to watch what I do, get comfortable with that, so that when you're finally on your own, you could do it for yourself, okay? So you might be tempted, but don't do it. Just go through the process with me. So the way we're going to begin is we're going to start by going over 7 rules. And during the process of these 7 rules, we're going to use a working example, something that we can interpret together. Then after that, I'm going to go over about 5 problems with you. And again, you're going to be patient and you're going to watch me solve it. You're not going to jump ahead. And then you're on your own. I'm going to give you about 15 problems to do on your own, and then we'll solve them together. Okay? So if you go along with this program, you'll be very comfortable on how to solve NMR problems. Okay? But just be patient and don't jump ahead of me. Okay, so let's get started. So here's our working example. It's pretty simple. It's 12 carbons. Here's our formula, and this is the chart that we're going to interpret. All right. Now, there's no IR. Sometimes they give you IR data. In this case, there's no IR needed, and what we have is what we need in order to come up with the answer. So again, I know you right now want to try, but don't. Let's go through the rules using this as a model. The first rule we have available is IHD. And let me emphasize, the order of these rules is not important. And you don't have to go through every one of these steps. It's not a step-by-step process. It's just things that you have available. And sometimes you might need 1 or 2 things and you get the answer. So it's not like you have to go through everything here, okay? But this is all the different things you have available to try to make it easier for you to solve the problems, okay? So just, go along with me on this little tour. IHD, remember, that's index of hydrogen deficiency, and what we do is we take our unknown formula, and by looking at our unknown formula, carbon count, we can figure out what the alkane should be. Remember, it's CnH2n plus 2. That's how you figure out your alkane. And since I know my unknown number of carbons, I can plug it into this formula. Now, our goal is to subtract and figure out how many H's are missing from an alkane. If you divide that number by 2, you get the IHD count. Now remember, IHD is like currency, right? So think of it as currency. It's like money. So if you want to buy an alkene, then you have to have an IHD of 1. If you want to buy a ring, you have to have an IHD of 1. If you want to buy a triple bond, you need $2, right? So it's all about how many IHDs. If you have 4 IHD, you could buy 2 triple bonds, you could buy 4 double bonds, you could buy 4 rings, you could buy a combination of these things. Right? 1 double bond, 1 ring, and 1 triple bond, and so on. You have $4. So you just think of it that way. Now, remember that you have to sometimes sanitize your data. So in other words, your unknown, if it has any of these here, halogen or nitrogen or oxygen, this is what you do in terms of sanitizing the number of H's. Remember, our goal is to figure out how many H's we're missing. But these 2 groups, halogen and nitrogen, they screw up your process. So we have to add things or remove things from our formula. So for example, if I have C4H10O, then I don't have to do anything with the oxygen. But if I had C4H11N, then I have to subtract 1 from that H count when I do my IHD consideration. Okay? Because every time there's an N, you subtract 1. Halogen, you would add an H. So you just use this in order to figure out the H count that you're actually working with. All right, in our case, we don't have any O or N or halogen, so we could just go straight from this. So C12 is the number of carbons in our unknown, right? This is our unknown. And so what we have is C12, H, now 2 times 12 plus 2 is 26. So we have H26, and we're given C12H 18. Now again, if there was an O in the formula, we ignore it. But if there was an N here, we'd have to subtract 1. It would be C12H17, right? But in our case, we're not doing that. All right. So how many H's are we missing? Well, we're missing 8 H's when you subtract this. Divided by 2 equals 4. So our IHD equals 4. So that means that we can have double bonds, triple bonds, ring, and so on. But we don't know. That's all we get from this first step. That's it. We just know that we have an IHD of 4. And we're going to keep that in mind. The next one is integration. Now remember, integration is usually given to you, so you don't have to worry about calculating it by counting the area under the curve, but it might be a ratio or it might be the actual number of H's, so you have to look out for that. Now here are trends that you must keep in mind. I wrote out a whole bunch, but really if you have 2 H's over that chemical shift, then it's a CH2. Okay, that's what you know for yourself. If you have 3 H's, it's a methyl. If you have 4 H's, then it's 2 CH2s. So how would you get a reading like that? Well, think about it. If you have a reading, and let's say you have a chemical shift here, and I write 4 H's, that means that there are 2 CH2s that are exactly the same, and they give the same reading on the chart. So you see, this tells me that I have 2 CH2s that must be either connected to the same carbon, right? Like maybe, for example, let's say there was a Br here and a Br there. Well, this is 2 CH2s that will give one reading, and so it's 4 H's, right? Or another thing is it could be symmetrical. So like, well, this is symmetrical. It could be like, let's say we have a reading and it says 6 H's right here. So now with 6 H's, it could be 2 CH3s, which is more likely, or 3 CH2s, which is less likely. But if it's 2 CH3s, then what that means is that we would have a carbon that has 2 methyls touching it, right? Or we have a straight chain and both ends are symmetrical. So what this is telling me, well, I just did the same thing twice actually. What this means is that there are 2 methyls either touching the same carbon or across if it's a bigger molecule, then they're symmetrical somewhere outside. Let me give you an example so I could be clear about this. Let's say, for example, we have a reading that has, well, let me show you a molecule. Let's say we have that. So it's CH3 here, CH3 there, CH2 here, and CH2 there. So I would have 2 readings on my chart, right? I would have my quartet, and I would have my triplet, right? Now here's the thing. This one here is split. So if this is A and this is B and this is A, right? Because there's a plane of symmetry in the middle. Now remember, B's won't split each other. That's why it's only a quartet. It's not a multiplet. Okay, now A is split by B, B is split by A. But if I wrote integration, it would be 6 H's and 4 H's, right? So I would know that this is 2 CH3s and this is 2 CH2s. So if you have 2 CH3s, it's either cross symmetry or they're touching the same carbon. And that's kind of what I was trying to show you here. This one carbon here has 2 methyls touching it. In this case, it's not that the methyls are on the same carbon, but they're symmetrical across the system. So those are the 2 possible scenarios. Either way, integration is a huge part of this, right? It really does dig in and help us learn things. Now, if you have 9 H's, it must be 3 CH3s. Okay, that's what it would be. So 9 H's on one reading means that there are 3 methyls either touching the same carbon or somehow it's symmetrical across. So keep that in mind. You could also have like 12 H's, right? If you have 12 H's, then that's 4 CH3s. Now you might say, well, why isn't it 6 CH2s? You'd have to have a pretty big molecule to get 6 exact same CH2s. It would be a very large molecule, so it's very unlikely. If you have 12 H's, it's probably more likely 4 CH3s. That makes more sense. So again, in that case, maybe you have branching methyls on both ends, and that's where the symmetry lies. But you get the point. So integration tells us the number of H's responsible. Oh, wait. The number of H's responsible for each chemical shift. Yep, that's right. So it tells us the number of H's for each